Very good.
So welcome back, everyone. Let's start with the second section for today. Basically, I'll be talking about research project management. So I'll be summarizing what Nicholas told us in the morning. I think it was really, really an excellent summary. I did not assume it is possible to pack almost everything into 2 hours, but I think he did a really excellent job. So this would be like a more practical approach to it. And I already introduced myself briefly. Well, one thing before I start with this, you can access all the slides and all the notebooks on GitHub. I don't know if you already have.
I'm going to send you the link, everyone. So, yeah.
So, yeah, all the slides of today and tomorrow and all the notebooks that we'll be using for tomorrow will be accessible from the GitHub. It's Machine Learning Tokyo/ELSI Learning. And you can follow along with the slides as well as with the code. Yeah, so in the past 2 years, I've been really, with NLT, I've been mainly mentoring or managing machine learning projects. So as a PhD student, I've been working on NLP and machine learning, but my main job with NLT is really making sure that the whole pipeline works, that from really collecting the data all the way to training models and evaluating models. And I want to share with you today like a couple of things that I've been experiencing in the past couple of years. And also from NLT is like mainly doing workshops for engineers. And in my own kind of academic career, I've been working very interdisciplinary on machine learning projects, working with linguists, cognitive scientists, psychologists, computer scientists, machine learning engineers. So today I want to share a little bit like what are the important things when you work in a team, as well as when you're maybe building yourself models. And tomorrow my team will join. So today it'll be only me talking a little bit about project management. And tomorrow my team will join. We'll be doing just a very high-level intro to deep learning, to deep neural networks, understanding what is learning in deep networks, how does it work, what are convolutional neural networks, and how do we use them. And then my colleagues will take over, and we'll be writing a little bit of code tomorrow. So Dimitris is a machine learning engineer. He's working at a medical AI startup here in Tokyo. He's mainly working with medical imaging, so things like he's working a lot with radiologists, domain experts coming from the medical field, on disease detection from pneumonia to brain scans. Mustafa was also working for a couple of years as an AI or machine learning engineer for a startup here in Tokyo. He now, I think half a year ago, he started his PhD at the University of Tokyo, doing satellite imagery. And Alisha is also working as a machine learning engineer, mainly in the object classification and detection for a Singaporean startup. And those three guys have been mainly doing the workshops for MLT in computer vision. And for us, it's always, there are many, many ways how to approach machine learning for someone who has never heard of machine learning. Our approach is very top-down. So we always do a little bit of theory depending on the level of the audience. And then we typically dive straight into code. I feel like the barrier should be very, very low to just try things out. There's nothing you can basically break. I know like in science and in research, we're supposed to understand everything before we actually do stuff. I think here it really should be, or can be, this is what I would recommend, just to try a lot of things out. And there are many reasons for that. I will talk about this a little bit later. So to understand, like, because I actually don't know anything about you, and I really kind of feel I need to know a little bit about you before I start my presentation. So for whom of you is machine learning completely new? Okay, that's good. So a couple of people know about machine learning. What about writing Python code? Who's writing Python code? Who has already built a machine learning model? Okay, that's good to know. So at the end of this two-day bootcamp, we were really thinking about how to approach this best to kind of give you maybe a first really good understanding of what is machine learning, could you be using it, could this be something you'll be working with, and if yes, like how do you build a team, how do you work on stuff, and it really depends on the level. So hopefully at the end of this bootcamp, you will have high-level understanding, some intuition about different learning approaches and algorithms in ML. Whereas I have to say, we will actually be less talking about algorithms, as Nick already said. It's not that it doesn't matter, but you will see that you will spending most of your time thinking about data, working with data, thinking about the problem, about the task, and resources and things like that. And especially like when you're in machine learning, like classical machine learning algorithms, it's very easy to do some experimentation, to switch out algorithms. When you use tools like scikit-learn, it's very, very easy to do a lot of experiments. So the main chunk of the work is really working on data and understanding the process and the whole pipeline as a whole. You'll also learn about tools and frameworks and libraries that make your life a bit easier. So I think for those of you who know Python, this you might already know this. For those of you who don't write code, this is something also like important maybe to know. And I'll give you like a couple of things that you might look into a bit deeper, and that makes it very easy to get started and to write your first lines of code. So today and tomorrow actually we'll be also writing machine learning code. So today we'll be looking at scikit-learn and some classical machine learning algorithms and pipelines. Tomorrow we'll be doing a little bit of exploratory data analysis, and we'll train our first convolutional neural network, a very, very simple network. And the last thing is, I think it's also really important by understanding kind of this pipeline and the process, you'll be able like to assess if this could be something for your research project, if machine learning could be a suitable method for your research task, or deep learning. So this is going to be really important. So we already heard about the most important things, I think, from Nick so far. So we heard about different learning approaches, mostly supervised learning, and I think it's important that we focus on supervised learning. This field is so huge that it's like, I think the most common and the most standard way for machine learning and deep learning is definitely supervised learning, and probably also the most useful for a beginner. In the context of classification or other things in computer vision. We also heard about different network types. We heard about critical thinking, like how to evaluate different things and how to assess a project. And the goal of this section will be just to walk you through an ML pipeline for your research project. The outline will be as follows. We'll be looking at machine learning in different scientific disciplines, or what does it mean like when we have machine learning in interdisciplinary research. We'll see like interdisciplinarity in artificial intelligence, collaborative research, and domain experts using machine learning. So there are many, many different ways how we can incorporate machine learning into our research. We'll be spending most of the time on data. We haven't talked a lot about data, but I think it's probably you'll be spending a lot of time on data. It doesn't matter if you're actually building the model or not, but data is the most crucial aspect. What you basically feed your model, that's what you're going to get out. So you want to make sure that your data is as clean and as good as possible. We'll look at collection and storage. What kind of data are we dealing with? Data set size, even though these questions are really hard, so I can tell you right away there is no number and there are no easy answers to any of these questions. but there's like some maybe guidelines that you can use for your own project. And when you're experimenting more and more, and when you're actually building models, you get more experience and you kind of get an intuition about how to build baselines, how big your data set should be, and so on. We take a look at pre-processing pipelines, very, very simple, like what are the steps that you should take when you want to pre-process your data, and very briefly how to reduce dimensions and how to visualize your data. We're not going to talk too much about algorithms because, as I mentioned, it's literally in scikit-learn. You're just switching out a couple of lines and changing the algorithms. And when doing grid search, you can very effectively search for the right kind of parameters. And I will end the presentation with a toolbox giving you like the libraries you can work with, tools you can work with, environments, and maybe like a couple of things that you can use to dive deeper into the matter. And on the right side, you'll see what is like the typical kind of pipeline when we are working on machine learning projects. So it all starts with the data and with data collection, assembly, and annotation. You have to do a lot of pre-processing depending on the problem, depending on the task, and of course, like the network. Data exploration and visualization. So you want, as domain experts, you already have kind of an advantage, right? You typically know your domain very well, you know your data very well, but you want to make sure that you know the specifics of the data set. So by visualizing, by inspecting it, you get a clearer picture of where you're at. And then actually the last two parts, so you see the most of the work is actually in the data field, and then building the model and evaluating the model, which is also can also take actually a very, very long time, especially when we're talking about deep learning and deep neural networks. This can be very time consuming as well. But these are the last two steps that you typically do. So sometimes like the easiest and the simplest thing can be the trickiest one, and especially if you haven't heard about machine learning, but hear all the buzz around it and hear all the hype around it, and are actually not quite sure what's AI, what does it actually mean, and I like to really kind of just, I know this is very simple, but I think to clarify those terms is really important. When we talk about artificial intelligence, this is a very kind of vague term, right? This encompasses everything that is related to machine intelligence. This includes things like rule bases, knowledge graphs. This includes things like, of course, machine learning and deep learning, but also things like very general computer vision, natural language processing, reinforcement learning, IoT, robotics, and so on. So this is a very big term that encompasses everything. And the reason why this is maybe also a reason why it is so hyped up, because it is very hard to define. Whereas machine learning is a very technical term. Machine learning is a subset of AI. And deep learning is a subset of machine learning. And what is different here from all these things that I just mentioned, or mainly like what is different compared to rule bases, expert systems, and so on, is that we have here algorithms that learn from data. So we're basically learning patterns from the data we give our model to, and we're mapping inputs to outputs, at least for supervised learning. And especially when we're talking about deep learning, we're talking about end-to-end systems. So very, very different from expert systems and knowledge bases, where we explicitly hard code features, where we hard code specific rules. We don't have to do that with deep learning. This is also, so Nick mentioned deep neural networks are very flexible. This is definitely one of the reasons why we need neural networks. And the second thing is it really kind of automates this tedious and time-consuming work of building rules and writing rules. In the field of language, for example, when I was doing my master's, I was supposed to be or become a computational linguist, and I had to choose between, am I going to write rule bases? So am I going to write expert systems, or am I going to write deep learning systems that learn those features by themselves? And it was very clear to me back then that language is basically the combinations of finite elements in language are infinite. So you can write as many rules as you want. It will never cover your data set, especially when we're talking about very, very large data sets. So I decided, instead of like using my domain knowledge and writing rules, I will focus on building end-to-end systems and designing data sets. So this is the main difference, and I think it is very important to understand this very, very clearly. So let's move to research and how we can incorporate machine learning into research. So the first thing I want to mention, this is very general, but I think it's really interesting to kind of see that it's not only hype, but there's really a lot of very interesting things happening. Interdisciplinary research in AI and machine intelligence. So we see institutes being established, like Stanford's human-centered artificial intelligence, where we see that they're really putting the emphasis on interdisciplinary and cross-disciplinary research in order to build very robust and stable human-centered AI systems that understand human language, emotions, intentions, behaviors, and interactions on multiple scales. And I think, to me personally, this is probably one of the most interesting things, even though I started out like really being a domain expert and just using deep learning to solve my own little kind of research projects and problems or problem statements. Now I feel like moving more into kind of this direction of interdisciplinary research for AI systems, where I've been working with different researchers coming from different disciplines. We also see this at MIT, but there are many actually examples that are now being established, and where you see that they actually put a lot of money into this. Where they say here, for example, the world needs even engineers that have like a very solid understanding of liberal arts and who can build like more ethical products and platforms, as well as policy making. So I think this is like one trend that we see in academic as well as in industry research of interdisciplinary approaches in AI. On the other hand, we also see collaborative research that is coming from different disciplines, including machine learning. In December, I was at a machine learning conference called LIRIPS, and this is one of the biggest machine learning conferences. It's a neural network conference, and they're also having like a very a focus on neuroscience, so it's kind of in between machine learning and neuroscience. And one of the talks that was given by Mike Leving was what bodies think about bioelectric computation outside the nervous system, and it was a really well-perceived talk. I think it was a really great talk. And those guys are biologists or computational biologists, and they are mainly looking at information storage and processing in biological systems. And they work together with machine learning researchers in order to get like a better understanding of their field. But as you can see, and maybe this is because it was a machine learning conference, there's also things that when collaborative research is being done, you can also kind of get some insights from systems, from biological systems, from neural systems, from cognitive systems, in order to use it for machine learning or deep learning architectures. So here on the right side, he also mentions that the bioelectric mechanisms of non-neural patterns could be like one potential direction to move from neural architectures in deep learning towards like different kinds of architectures to build more robust systems. So really interesting research that is collaboratively achieved. So basically, it's either like the domain expert that is using machine learning, or in this kind of way where it's giving insights into for machine learning systems. I really highly recommend this this talk. It was really great. We also see collaborative research in medicine and healthcare. I think this is one of the maybe most promising directions where we see great efforts being made that actually are applied and help people. So this. Okay. So this is the Lab of Medical Imaging and Computation, and it's a collaboration between the Massachusetts General Hospital and Harvard Medical Schools. I know people there at Harvard Medical School who are actually using machine learning themselves, so it's really great. And this is not only in research but also deployed in industry. And I think it's really, really fascinating how machine learning and deep learning can be used to really make a difference. I just mentioned here a couple of things: organ dose estimation, bone age, hemorrhage classification, breast cancer, all kinds of things like pneumonia detection. Yeah, and Dimitri's tomorrow is who's going to be here tomorrow is also working in that direction. So I think this is really really interesting stuff. On the other hand, we see domain experts using machine learning, and this really, we can see that in all kinds of different directions, from natural sciences to social sciences to applied sciences. I just mentioned here two papers, one in genomics with kind of a primer on deep learning, and the other one for cognitive neuroscience. And here again, if you read this paper, deep learning for cognitive neuroscience, I'm not sure like how much is like really hype and trend, like using cognitive science or neuroscience to really advance the field. We just talked about it. It's really hard probably to get insights from neuroscience and to build better architectures, for example. But there is definitely research going on in this direction, and I think it's very, very interesting. On the other hand, we also have, as I mentioned, like domain experts using machine learning. These are just two examples where we have deep learning for crater detection. The first example is lunar crater detection. They're using region-based CNNs. And the other one is a friend of mine. She just graduated her PhD, and she wrote her thesis on segmentation with convolutional neural networks for automating crater detection on Mars. So these are the things that maybe have some applied value, because this used to be like a very kind of time-consuming work to label all these craters, to count all these craters by hand. We already heard it, students, and this is only one example. There's literally so many examples of students labeling and annotating data. So this could be one way to use deep learning to really help speed up the process and to automate basically that the task away. So you might think like we're automating work away, but I think nobody likes doing these kind of repetitive annotations. And I think you are on the paper, right? Mm. Yeah. So this is kind of a very good example of collaborative research where Danielle, for example, who wrote her thesis, I think her background is in space engineering, and she started getting into deep learning. Like she understood like there is a problem. We're having this sort of, we have to do this annotation, this counting, and it takes a lot of time and a lot of effort. And there are very simple methods, very well-established methods in deep learning for detection, for example, and counting, building those bounding boxes that are surrounding the crater. And this is really a great opportunity to build something that can help automate that basically away. And I asked her like, how did she approach this? And it was really also top down. getting into deep learning, just writing code, experimenting, using something, and we will take a look at it in a bit. A high-level deep learning API called Keras. It makes it very, very easy to get into and to just experiment a bit, and then gradually improve and progress. I think it's a really great example. And I'm not sure, like, what was your part in the, because she was actually building the model herself, right?
Yeah, so we started out, she hadn't done any machine learning. So we did something like this with some example code and so on, and then she went and developed and fine-tuned it and tried 20 different architectures and 80 different hyperparameter sets and validated it and all the,
Yeah. And you were mentoring or supervising.
Yeah. Meetings every month.
And how do you feel was that top-down approach when she was just getting into code, experimenting?
No, yeah. The thing to get into is like this idea of code grab, read papers.
Yeah.
That was, I think, the jump. And once there was code, it went.
Right.
Although there was also a delay where we didn't realize the default layer in Keras is linear, not real.
Oh.
So we were doing fully linear CNNs and wondering why they weren't doing any better than.
Really?
Yeah.
Oh. Yeah. Yeah, as I mentioned, like there are many different ways how to get into the field. Sometimes, and I think also like because we're in Japan, of course you can learn everything about linear algebra and you learn everything about multivariate calculus, and then you learn everything about architectures and the math that is underlying certain models. And then start slowly like getting into code and writing code. This is definitely one option. So if you feel like more comfortable and more confident in math and applied math, absolutely. I think for really the vast majority of people that I have seen coming either from industry or from research, it's really kind of top down. So the first thing, you kind of know your data, you know your task, and then you just go and experiment. I know this is, kind of a bit risky, and you don't know what's going to happen, especially when we hear things like black boxes and we don't know what's happening, things like that. But me personally, I read a lot of machine learning papers, and before I actually started writing code, but it was completely abstract. So there was nothing like really concrete that I could apply the things that I read to. So when I actually started writing code, it made all the difference. Things really kind of started to make much more sense. How you transform your data, how you shape your data, how you feed it into your model. Like when you do linear algebra, it's going to be very theoretical and very dry maybe, but once you actually build your network, you do understand, okay, so that's why I need to do that. So it kind of makes a lot of sense to just jump into it and write some code, and that's exactly what we're going to do tomorrow, and today actually. So data. We already heard a little bit about data. There are many different kinds of data that we're dealing with. There's columnar or tabular data. We already heard about that. Images, text, audio, video, like basically any sensor data, anything you could feed your any kind of data, really. So I'm curious, what kind of data you are using? Who here is working mostly with columnar data? 2, 3, 4. Okay, 4, 5. What kind of data is that? Can you tell me?
It's like atmospheric reaction rate data. So it's like looking at like a chemical network that I have, how they relate to each other, and then looking at the kinetics and seeing how far it takes us in the reaction chemistry that I did.
And what would you trying to figure out with that data?
We're trying to basically figure out if we need to add in, because the atmospheric chemistry, we're looking at abiotic factors on like for biosignatures. Except this would be a new type of biosignature. So it's looking at it and saying like, okay, so we have these pathways. There are some pathways that we don't know. Can machine learning programs see this pathway that we think might exist, but we're not sure?
Mm-hmm. I think you were one of the people that said you have a little bit of experience with machine learning.
Yeah, I mean, I have some experience with like MATLAB and Python.
Okay, that's great. Good. Who is working with images? Nobody? 1%? Yeah. What kind of images?
Maybe sometimes with like, microscopic images, including TEM and ACM images.
What kind of properties do these images have? Are they color images? Are they grayscale? Do they have like very distinct features?
So, for example, for the transmission electron microscope, microscopic images, you can get the very clear lattice information. Like I'm dealing with the crystalline material, and then you can get the crystalline phase, and which is the crystalline phase that you are observing. This kind of information.
Mm-hmm. And what would you want to do with this image data? Would you classify something? Would you detect something, put a bounding box around it?
It's like I want to see what's the crystallinity, firstly. Like what's the two-dimensional order of the observed part. And also I would like to know what's the exact crystalline phase that I'm now observing. And also the phase boundary structure.
Okay, cool, nice. So, okay, we have images in tabular data. What kind of data are you working with if it's not images in column? Anyone? Yeah?
I'm working on the scientific record. I would say shows some features with the audio data.
Okay, nice, interesting. Sequences. Yeah. Nice. Cool, okay. Anyone else want to share? Yeah?
Yeah, like biological data. So if you have a particular organism, you might have some reactions which you can analyze, or you know the number of reactions which you can analyze with different organism. So generally, tabular data sets.
Oh, I see. Interesting. Yeah, so there are all kinds of data. It's interesting that it's very, very diverse. We'll be doing images tomorrow, but yeah, I think that's the reason why this should also be just give you the big picture of understanding like what is the pipeline, what is the learning process, what could you be doing. So understanding this will help you actually a lot getting into your own task and your own problem. And there's no one answer to there's not one model that fits it all. There's no one answer that kind of answers it all. Just one more question. I'm curious, what is your data set size, for example, that you're working with?
Oh, the size?
Yeah. How big is it?
Several megabytes.
Several megabytes?
Yeah.
How many images?
How many?
Yeah.
Actually, I haven't like fits my project into machine learning, and this time I just have interest in this.
Okay, cool.
I think that my data is not that huge.
Yes. I think that's mostly the case, right? And we will see later on. When we talk about deep neural networks, they're sometimes trained with millions of images, right? And when we have very small data sets, we need to figure out how to deal with that. Because our model is only as good as the data is. And when it's very small, it's going to have a very hard time to generalize very well. So we need to use like different kinds of techniques when we have small data sets, or maybe go into the direction of the classical machine learning algorithms. What would be your data set size? How big is it? What would you say? How many observations?
Usable data-wise, it's probably like 300, 400 entries, not much.
300, 400 entries. Okay.
Because there's data that's available. Like there's obviously data just on like my specific chemical like nitrogen. There's like 900 to 1,000, but it's not like getting the tabulated values that are usable in research, like papers, is different.
Cool. So it's also really interesting for us because we've been doing a lot of workshops and trying to figure out machine learning projects for different kinds of tasks. So it's really, and we've been doing this, or we will be doing this with a couple of universities coming from very different disciplines. So it's very interesting, like to hear that, and maybe we're also talking to ELSI like to have more study groups or workshops coming up where we can dive into more details of certain tasks, certain algorithms, certain data types, and so on. So yeah, so basically all kinds of data, from these very traditional kinds of data or data types to anything you can imagine, sensor data, and so on. And when we're talking about deep learning, then the real kind of power of deep neural networks is really in the field of imaging, text, audio, where you have sequences or fixed size vectors as images. So this is typically where you would go into the direction of deep learning. So it very much depends where your starting point is. But typically, when you start from absolutely from scratch, you need to think about things like data collection, data annotation, and data storage, especially when you're working in teams. I'm not sure like how relevant this is for this group, but we typically spend a lot of time thinking about these things, and this can be more or less very, very sensitive as well. When we're thinking about language data, social media data, medical data, like all these kind of anything that involves humans, we need to be very careful with how we collect data and how we annotate data. On the other hand, yeah, there are a couple of things like when it comes to collection and annotation, like what kind of annotation scheme do we use? What would be the appropriate annotation scheme? What kind of resources do we need? Luckily, and I will talk about this more tomorrow, we have in less specific maybe contexts, we have a lot of great resources and platforms to kind of access data sets and also annotation. So I'll talk about this later or tomorrow basically. And the other thing that we need to think about is when we're working collaboratively. So some of you might be actually building the machine learning models yourselves. Some of you might be working with students or postdocs that will be building the machine learning models for you or with you. In any case, when you're working collaboratively, there are a lot of things that you should keep in mind. For example, how do I store my data set that is very easily accessible to the whole team, for the whole team? Includes things like download scripts if necessary. Format is always a thing. You know, typically when you have data and you get raw data, it is very messy, it is very unstructured, depending on the data source. So you need to make sure like it is very easily accessible and in the right format for the whole team. And as I already mentioned, sometimes you have very sensitive data that you need to be careful about. I'm not sure how it is with Earth Life Sciences, maybe not so much. I don't know if you open source things or if things are openly accessible. But generally also in machine learning and in machine learning research, when we deal with data, there's a lot of value actually to open source data sets, to benchmark data sets, and to let a lot of people work on it. This will not only help your own research, but also other people's research. So there's a lot of value actually in open sourcing data. Not sure how it is here, but maybe something to keep in mind. Yeah. So I just took a very simple example, and this has nothing to do with your research. But what I want to say with this slide is that we have, when we compare these data sets, you can see that the complexity varies in a lot of different senses, right? Or from a lot of different perspectives. The question is, how much data is enough data? And this is very hard to answer. You gave a very statistical. It's very hard to tell. It really depends on so many things. And I just have here a couple of data sets that are very typical, very traditional image data sets that are used for machine learning. And if we just take a very brief look at it, we already see, okay, there's like major differences. On the left side, we see cats and dogs, right? This is a binary classifier. So we basically just want to distinguish cats and dogs. We want to build a model that can successfully identify a cat or a dog. So we have two classes, right? And this actually, when we do this in practice, if we would scrape a data set of cats and dogs, and we would run a very simple algorithm, a very simple CNN, you would actually see that you don't need that much data. So you absolutely don't need a million images. You need maybe, maybe 1,000 would be enough to build a really good classifier. A really good binary classifier that distinguishes cats from dogs. And we also can see the kind of the pattern complexity between a cat and a dog is okay, right? Just by looking at it. So as a human, we could, in most cases, maybe easily identify if it's a cat or a dog. And typically, what we can very easily in a second or so identify, it should be doable for the network as well. At least this is what Andrew Ng says, and Andrew Ng is like one of the most reputable professors at in machine learning. So the next data set is the Embeddings data set. This is probably like the most famous data set in machine learning. This is a data set of 60,000 training images and I think 10,000 test images. And you see it's like a lot different, right, from the first image data set. First of all, it's grayscale. This makes actually quite a difference. So we only have grayscale, which makes the problem and the task a little bit easier. But on the other hand, we have 10 classes. We don't have 2 classes. We don't have a binary classifier. We have a multi-class classification problem. So we have 10 probability distributions when we get our first prediction. And we have to choose the highest probability, so the number that is to be most likely the correct number. So as you see, like here, the task might be a little bit more difficult, but the patterns, it's grayscale, so what we have actually is a little bit easier. One more thing, I think Nick also mentioned this, resolution. It also determines like how hard a task is, how hard it's going to be to train a model or not. If it's 28 by 28, it's very low res. So it should be, in theory, it should be very easy to train. And the fact that we have 60,000 training images, we should be pretty confident that this is going to yield like good performance. And it does. The next data set is the CFAR10. These are the same classes as we had before, right? So we have 10 classes. So it's kind of the same level of difficulty you would think. But we have a completely different setup, right? We don't have grayscale, we have colors, and we have different kinds of stuff such as planes and cars and birds and cats. And again, we have 60,000 training images. So generally, if we compare it to the Embeddings, it should be a little bit more difficult. We have 2 more data sets just to demonstrate. ImageNet is probably the most famous data set in computer vision. And I think the original, the big one, is 20,000 classes, which is a lot more difficult probably. But we also see that the data set size is very different, right? We have 14 million images for 20,000 classes, and we have an average of 469 by 387. So this is quite a hard task. And not only it's hard, but the main thing here is this is going to take a very, very long time to train. So typically nobody trains ImageNet. We use pre-trained models. So we use basically weights that are already pre-trained that give us a certain score, and then we use those pre-trained values to initialize our model. So you can see like there are different. There is not one answer to this question, right? It very much depends on the data. It very much depends on the task. And this is all classification, except maybe for the last one, the Celeb A is mostly models where you don't necessarily classify as a celebrity, but you're trying to reconstruct a celebrity. But this is for generative models. But you see there's very different kinds of complexities that will determine a lot of different things like your data set size, the model that you're going to use, your baseline that you're going to build. But also you can predict, you already have some sort of intuition by just looking at these numbers, how long it's going to train, how difficult it's going to be, and so on. So again, just the questions that you could, like, even before you touch, you write any kind of code, is just thinking about your data and thinking about your task. What is my task? What do I do? Is it a classification task? How many classes do I have? Do I have 2 classes? Do I have 20,000 classes? Are the classes balanced? Do we have, what's the number of images that we have per class? Is it highly imbalanced or is it balanced? This also plays a crucial role, as we will see tomorrow. What are the distinct features if we compare the classes? How complex are the patterns, the color palette, the resolution, and so on. And this will help us understand how much data we need, what's our baseline model, at least get like a first kind of direction where we'll be headed towards. I also think, like, I've been working in industry for a bit, and I'm working a lot with MLT, with people that are in startups, and there's a lot of value actually in having domain experts that give you some insights about the data you're using. This is I would like even say in almost all cases the fact. So as I mentioned, Dimitris, for example, he works at an AI startup in the medical imaging, and they work very, very closely together with radiologists to evaluate the whole process, from data collection to data annotation to evaluating the outputs of the model. So it is very, very important, like, to work closely with domain experts. And us as domain experts, we have the advantage that we already know the properties of our data, the distribution of our data, and know, like, a little bit like some very valuable insights that you can use in order to build the most efficient models. So now we're actually at the point where we start writing the first code. And we start by pre-processing our data. And this is incredibly important because, as I mentioned, there's this one famous line in machine learning: garbage in, garbage out. So the messier and the, if your data is irrelevant and noisy and unstructured and not well prepared, not well cleaned, is whatever model you're going to use. If you use a 50-layer deep neural network, it's not going to give you anything. So it really is very important that you work with your data, that you prepare it well, pre-process it well, clean it well, in many different domains. I can tell you from a language perspective, I don't know if that's interesting, but you literally spend most of your time on that, because when you scrape social media data, text data, web data, it is like full of, like, it is very noisy. It's a lot of different languages, a lot of like weird stuff. So you need to be very careful about pre-processing. Maybe in your cases, if you already start with very clean data, I'm not sure. But in any case, you will spend some time on pre-processing. So as you see, maybe some fields require more of this, and some fields might be requiring less of it. So a typical, very, very simple kind of pipeline of pre-processing would look something like this. So the first thing we need is our Python environment, right? So we need to start writing code. And we're importing our libraries. And I'll get to that a little bit later, like what kind of libraries you can use and what will make your life a little bit easier. We'll import our data set. This is saved either like locally, or if you work on Teams, it could be somewhere on GitHub or in the cloud. And in step 3, we're starting to inspect our data. So what that means, and we start to plot it, because we need to, sometimes our data is so big that we cannot possibly say anything about it. So the examples that I showed you with ImageNet and things like that, you can plot subsets of it, and you can get some like intuition. But typically, when our data is so big, we can't tell like too much about it without writing code and without looking into it more deeply. So, for example, you look at your size. What is the size of my data set? What are the features if you have columnar data? What are the labels? How are they distributed? Are they balanced or not? What is the number of labels? Like many questions, to answer as many questions as possible to have an understanding of where you're at. And this will also help you like build your architectures. Like if you know, for example, what your labels are, if you have a multi-class classification system, you have to choose a very specific hyperparameter or network architecture in order to, for example, you have to pick a specific loss function. You have in your last layer, when you do deep learning, you have to specify if you're having a fully connected layer or a different kind of layer. So these kind of things will give you already some insights about how your data set looks like, what is the distribution of the labels, and also like a few hints on how you actually choose your hyperparameters for the network architecture. Again, like I think for in my case in language, this is really crucial because you need to specify a lot of different parameters based on just the pure inspection of how your data is constituted. Step 4, when we're dealing with columnar data, one of the major things is you're going to encounter missing values. Pretty much, yeah, that's pretty much inevitable, I say. And you can use techniques to solve that. So your model is never going to take an input with missing values. So you could use different kinds of techniques and libraries to alleviate that. So things like you take the mean, for example, of a column and so on. But you need to take care of those missing values, or you drop them. But well, in theory, you could drop them, I guess. But the least thing you want to do you want to drop them if it's too much. Yeah, you want to drop them if it's too much. But if it's not too much, you better fill them up because the least thing you want to do is take away information from the network. So you want to give it typically as much information and as much data as possible. So maybe fill it. And you could probably. The other thing is, so when we have columnar data or tabular data, which some of you guys are working with, we don't have necessarily only numerical values. So we do see sometimes, depending on the data set, categorical values, which could be some labels, etc. So we also need to transform these categorical variables to one-hot encode them and transform them into numerical values. Because your network, again, is not going to take anything that's weird as input. So we need to make sure all the missing values are filled up and your categorical values become numerical representations. Another thing you need to do is to normalize your data, to normalize your values, the variables. There's a technique called feature scaling, and so there's different ways to do that, but mainly you want to bring all your values, for example, between 1 and 0. That makes it easier for the network to train on. And then we finally get to the point that Nick also mentioned and explained very thoroughly. We split our data set into our training set, into our dev set, and into our test set, and feed it into our model. So this is also one part of data inspection or data exploration, exploratory data analysis. I mentioned it before. You typically want to know as much as possible about your data in order to make the right choices for baselines and network improvements and so on. So another kind of technique that is used quite commonly is different kinds of dimensionality reduction techniques. So here we see, in order to be able to plot our data, we can use different kinds of libraries. Matplotlib for Python, Pandas, and Seaborn are, I think, the most commonly used libraries. Pandas actually it's not a plotting library, but it's a data exploration library. So it allows you to read in data and display it, especially if you work in Jupyter notebooks or in Google Colab notebooks. It displays data frames, which makes it very easy for you to do exploratory analysis and that kind of things. And it really provides super nice different kinds of techniques to explore it more deeply. I don't know. I just asked like who knows how to write Python? Are there, because you might have like some background in statistics. Anyone using R? No? Okay. So this could be also one option. I think people with a statistics background who do like more traditional data science than machine learning probably are more familiar with R as a language, and you would use like different kinds of libraries and setups and things like that. But the most commonly used is probably Python. So those are the three libraries that you would use for visualizing your data. And we will see in the afternoon how this actually looks like when we write code. Yeah, I mentioned dimensionality reduction. So typically, with machine learning and deep learning, we work in very high dimensional space. So it's very hard for us to visualize. As humans, it's very hard for us to visualize, but it is very important because it gives us another way of looking at our data. Reducing the dimensions basically means it's the process of reducing the number of variables, and we're obtaining a set of principal variables or components. So there are many different ways to do this. One way would be feature projection or feature extraction. And again, there's like many different techniques you could use. I think the most prominent one would be PCA that we already mentioned today, but there's many more. Tomorrow, Alisher will show us how to write PCA and also TISNE or TSNE. I call it TISNE, I'm not sure. TISNE is it also a tool like to visual high dimensional data, and it's the interesting thing is that it might give you like very different results based on your initialization. So there are like always advantages and maybe disadvantages to everything that you'll be using, but it might be good like to plot something like a PCA just to have an understanding of your data distribution visualized and in a very low dimensional space, as you can see here in a 2D space or in a 3D space. Another thing that you theoretically could be using, and we already heard about this, so this is unsupervised learning. This would basically just be you feed it your training data and just see what kind of clusters it gives you. This is probably I wouldn't use that so much in a supervised sense. I would reduce the dimensions, but in theory you can use it. And there are different kinds of algorithms. So these are clustering algorithms, and based on kind of different properties, for example, like we want to cluster data points that are very similar to each other, right? That are very close to each other, and that are only in one cluster and not in the other. And there are different algorithms, which is I think the most popular one or most commonly used one is k-means. It's certain centroid model, so you pick the number of centroids and you cluster basically what's surrounding the centroids, and this will also change, right? So the number of k you give it, it's probably going to cluster differently. So yeah, drawbacks in everything you do, but it's a very important kind of tool to give you another kind of perspective of your data. If you want to know more about this, yeah, scikit-learn is your best friend. You can find everything in the documentation really explained. Okay, so up until now we talked a lot about data, and we still haven't talked about algorithms. And there's a reason for that. So you see that you'll be spending a lot of time thinking about your data and your task, and the different algorithms that you see here, and this is just a very small sample of algorithms that are out there. There are like tons of algorithms out there, and we could spend a whole bootcamp on each of them. So the underlying math, especially on the right side, is very complex, and we can talk about this for a very long time, I think. I think the important part is really getting the pipeline straight, understanding the data, formulating the problem, and then you typically have some sort of insight of how you will be building your baseline. But again, this depends just on many things. On the left side, you see some machine learning algorithms for regression and classification tasks. And this could be your main algorithm. This could be, solving your problem. And again, it could be just a baseline, just a reference point for you to improve upon. Typically, what we see when I look at, well, it depends. In industry, in CAGR competitions and things like that, we do see algorithms like that perform quite well and being very robust and giving very robust results. And there's value in that. So it very much depends on, I think Nick also mentioned, like when you evaluate your results, it very much depends on a lot of things. Like if the most important thing might be accuracy for you, and if you would want to compromise on complexity, training time, and so on to get that really squeeze that 1% out, then you might be really going into the direction of deep learning instead of like very classical machine learning algorithms. But if that 1% really doesn't matter too much, if all you care about is building a very robust, very understandable and transparent algorithm that gives you solid results, it might be better like to go for a machine learning algorithm. And luckily on the left side, the experimentation process is quite easy. So once you prepared your data, you know the direction, you know the task, you know what to do. It's quite easy like to do something like grid search or random search, not only like to see and to take a look at the optimal parameters, but also take a look at algorithms. And we have regression and we have different kinds of classification, even though there's many different variants. So you could, in theory, you could do a support vector regression as well, in addition to a support vector machine for classification tasks. One of the algorithms that really performs very well lately in competitions is something called XGBoost. It's a gradient boosting algorithm. Very, very robust, and sometimes even really is leading leaderboards on Kaggle. Do you know Kaggle?
Sorry for the interruption. Can you explain more about the baseline thing? Sure.
So let's assume we have a pipeline, right? Everything is ready. We have a train test split. We want to feed it to our first model. We need some point of reference, right? So we can't just say, oh, okay, let's start with a bidirectional long short-term memory network that does this and that. We need the first thing we need is to build a baseline. So typically what you would do is you would use an algorithm that you know is stable and robust and gives good results. You just try it with your first algorithm.
Okay, I just can like explicitly form a concrete idea about what the baseline is. Can you give me some example about in the case that you shown before? You want to supposing we want to distinguish between dog and cat.
Yeah.
And then what will be the baseline?
Okay.
Specifically?
Yeah, sure. So okay, let's say we have a binary classifier. We want to classify cats and dogs. So the first thing you want to build, you can even go like more simple than that. You build a very simple neural network. Typically, you would know. Okay, we can build like a very simple CNN, right? We build a convolutional neural network, and we use a very simple architecture. We use a 1 or 2 hidden layer architecture. We use certain parameters. And we just get the first results and evaluate the results. And these are our first results. This is our baseline, right? And then this is your point of reference where like everything that comes afterwards, you will compare to this baseline. Every like other parameters that you test, architectures that you test. We'll see this tomorrow. You will compare to your baseline. If it adds value, you will go this way, right? And you will try to improve on this. So the baseline is basically just the maybe not the simplest you can find, but the most representative and a good solid starting point for your
Very
problem.
sure. So some data that we are very sure about the input and output.
It's more like the algorithm. Yeah, it's more like really let me give you another example. So if you have tabular data, right? So the first thing you really want to do is you don't want to build a 50-layer deep neural network, right? This is maybe the last thing you're gonna do. What you're gonna build is a support vector machine, or even simpler, you build a logistic regression or something like that. So you build a very stable, good, solid machine learning algorithm that is not so expensive, right? That is not so that doesn't require like a lot of effort, but just to have a point of reference, and then you build up like upon that first baseline with different kinds of techniques, like grid search and random search. Yeah, I think that's an important point. Another example that I could give is, so what we would assume, right? We would assume that deep learning would always outperform a machine learning algorithm, but that's not the case. As Nick mentioned, deep learning scales really well when we have like a lot of data from like a certain point. But when I wrote my first journal paper, I had to write, I think, 42 architectures on. It was a comparative study on very small data sets. And our baseline models were these kind of support vector machines. So very, very simple, no feature engineering. It was grid search, so we did grid search the optimal parameters. It was so strong on the small data sets that it was really hard to beat the SVM baseline with a deep neural network. But on the other hand, what you can do is you can build those deep neural networks and use other techniques. So as I mentioned before on the image data set, even if you have a small data set, you can kind of use pre-trained networks. You can use transfer learning, where your network actually, where you use just the weights. So there was a completely different network that was trained on a much larger data set. Or you could use that for transfer learning or pre-training, and you just take that weights and you initialize your network with that. And that actually can help, yeah. But we'll talk about that tomorrow in a little bit more detail. But yeah, that's very important. Build a really solid, robust baseline. So actually one thing so a couple of months ago at LT we had Francois Chollet gave a talk. Francois Chollet he built one of the most famous deep learning libraries or APIs. And he said that any problem can be solved with deep learning if you just scale it enough. If you give it enough data, if you give it enough computational power, any problem can be solved. You can update your parameters until you convergence. It can be solved if it scales really, really, really well, or if you scale it. And it might be true. I don't know. I don't know if it's true or not. We can't really verify that, right? How much data is enough data? We don't know. But yeah, so these are always trade-offs that you make, right? And these are so if you don't care about state of the art, if you are not writing a machine learning paper where you need to beat a network architect or a benchmark for 0.1%, what you really want to be looking for is the most, well, depending on your task, but a good network that gives you good performance, thinking about the things where you might have to do trade-offs, right? So in deep learning, sometimes it's not even possible, right? So we need a lot of computational power to do very deep networks on very large data sets. As students or postdocs, sometimes we don't even have access to that kind of computational resources. So there's always this kind of trade-offs. that you have to make. Let me see. Yeah, I think I mentioned everything. Yeah, and generally, I think deep learning, for the reasons that Nick also mentioned, work just because they're flexible, because they have very certain architectures that taking either variable length sequences or images as input and process them and extract features very, very well as end-to-end systems. That's the reason why we see deep learning architectures really giving state-of-the-art results for many different tasks in computer vision and NLP. So one thing that you might have realized is that I only talk about deep learning and images and text and video and audio and not really about tabular data. It's not really that common to use deep learning for tabular data. We do see it now. Like some people have been working on it, but typically you wouldn't associate deep learning with tabular data. So if you are working with tabular data, it might be a really good idea to explore machine learning algorithms and see how that works. And if you would need something like more complex, you can always look into deep learning. So yeah, how do you know your results are good? That's really good. Good is always relative, right? So we heard it before. It very much depends on the task, on the severity of your task. But in principle, first you build your baseline and you improve upon this baseline. So this will serve as a reference point, as I already mentioned, for comparison with different setups, algorithms, parameters, architectures, and so on. And if those changes are adding value, it's probably the better way, the better thing to do. How do you evaluate if results are better or not? Yeah, it very much depends on what is important to you. Metrics, right? We have very different kinds of metrics, and depending on your task, you want to evaluate a classification or a regression result. You would choose something like the mean squared error or mean absolute error for a regression task in predicting continuous values. You will want to go for accuracy or F1 scores for classification tasks. But it also depends on like even if you do F1 scores or precision recall and things like that, if we think about, and you already mentioned it, right? If we think about the medical one, you really, really want to focus on, it's called specificity and sensitivity. These scores are very, very important scores for you because you want to avoid false negatives as much as possible. This is like the thing that you care about the most, right? You don't want to get this one wrong. So it very much depends on the nature of your task and the severity of your task and so on. In some cases, it also, efficiency and training time and computational resources and so on do play a very big role. Probably especially in industry where they want to minimize costs as much as possible. From a research perspective, we just sometimes don't have the resources to do very large-scale experiments. So you kind of need to figure out what is the most efficient way for building machine learning models for your particular problem. And sometimes, yeah, as I already mentioned, you will take a slightly lower accuracy, like not having to really train very, very deep, very expensive networks. Okay, so this is the last section, and is it the last one? Yeah, it is the last one. So these are a couple of things that we work with, and it's not all of it, but this is really a good start, maybe for you to get more into it. And as I already said, I think it's really great to just jump into it, try out your first thing, and we will actually in the afternoon. So please just get into it and write some code. On the left side, we have some machine learning stuff. We already heard about scikit-learn. It's a machine learning toolkit, and it's your best friend. It's very simple. It's really simple. You will see like once you have your data pre-processing pipeline and it's split into your train, dev, and test set, you will see that it's literally switching out 1, 2 lines of code and experimenting with different algorithms. And this is a really good start. I'm not saying that this is your end point, right? I'm saying this is your starting point. Experimenting with stuff is important because a lot of these things you will see. I think somebody asked the question today, how do you know which parameters are good? A lot of these things you do through experimentation, either by yourself or you read papers and they do very large scale experiments and you see that they figured out like the best parameter values for certain networks, for certain tasks. So experimenting is a huge deal for machine learning, even though it might not sound like super scientific and not being able to understand everything in detail, but it's a great starting point. Once you experiment and once you get a feel for what is needed, how the pipeline looks like, how do we write algorithms and things like that, you can specifically for your task and for your field and for your data go deeper into the things that you need, because you will not need all of this, for sure not. You will need parts of this for your specific tasks. And I think it makes a lot of sense to experiment and to get your hands dirty and then really kind of go into the details afterwards. That's what I would recommend. So this is scikit-learn. We'll see it in a second when we write a bit of code. For visualizing, I already mentioned Matplotlib, Seaborn. What was the other one? Oh, Pandas, yeah. Pandas. And Pandas is generally like a data analysis kit. So you can plot things, but you can also really look at data frames, slice things. Yeah, it's really, I think without Pandas, I don't know what else. It's really probably the most, I love Pandas and NumPy. Those are the two most important things. On the deep learning side, yeah, it's NumPy. It's a scientific computing library. It's super fast and super awesome. You do all your matrix multiplications with NumPy and don't have to worry about it. And other cool stuff and transformations and stuff. So these are the essential things. You will always need them. In terms of deep learning, we're very lucky that we have very amazing frameworks, very well documented tutorials that will make the barrier is very low to actually getting into deep learning. It's the same for machine learning. So really the barrier is very low. It is extremely well documented. It is extremely easy to follow, and there are standards. There are a lot of standard examples that you can just use. All the things that we mentioned, all the algorithms, all the tasks from binary classification to multi-class to multi-label. Like there's a lot of different tutorials out there that makes it very easy for you to actually get started. Some of the most famous frameworks for Python are TensorFlow. It's a Google framework. It used to be very complicated, actually until recently. So the learning curve was quite steep. It was very difficult to get into. Now they've released TensorFlow 2.0, which is much easier, much more intuitive. So definitely worth looking into. TensorFlow is mainly used in industry. This is kind of production level deep learning where you deploy your deep learning models to production. PyTorch, on the other hand, is probably more used in research. I think most recently, like a lot of researchers really love PyTorch. It makes research very easy. It's also very well documented. I don't work a lot with PyTorch, but I really like some properties of it also. It was built on top of or inspired by Torch. And then there's Chainer. Chainer is a framework that was developed in Japan, in Tokyo, by Preferred Networks, and it's also very popular in Japan. And probably most of the universities here in Japan work with Chainer, as well as industry labs. One thing that I would really recommend, this is also, I remember that you said, so Danielle, if you remember the PhD student or the PhD now at Todai who got into craters, into Mars craters, started with Keras, right? And I believe it's really the most simple way to get into deep learning. It's very intuitive, it's very simple. The problem is it's very implicit. So if you build your models, and we'll see that tomorrow, you can build your models without really having to explicitly write out things. So it will do a lot of things for you implicitly. That makes it easy to get into, so really great for beginners. But it's less flexible. Now it is more flexible, but it was less flexible than, for example, PyTorch. And I think you mentioned that you would have chosen PyTorch over Keras now.
Yeah.
Yeah. Why?
Well, in particular, in that thing, some of the implicit stuff, we had linear layers for 3 or 6 months, and just didn't notice it because we thought the default was 3D. So all of the time, linear libraries were just like giving the same performance no matter what the architecture was, because it was just linear algebra.
Yeah, so basically you just call a layer and you don't really know, unless you really go into documentation code, what kind of activation functions are used and so on, even though they are standards, right? If you use an LSTM, it's probably going to be standard.
Yeah, that's a specific anecdote, but I think more generally, if you want to do things that are even slightly non-standard, you start to fight libraries pretty quickly, and in PyTorch, you're able to access the lower-level stuff a little bit more easily than you do with Keras.
That is true, yeah. That is true. However, with the new TensorFlow release, and TensorFlow and Keras, they kind of go hand in hand, because Keras is just an API, it's just a library, and it needs to run, it needs a backend. So it typically runs with the TensorFlow backend, although you could use probably any kind of backend, but typically it runs with the TensorFlow backend. And when they did the new release, they really released a couple of really awesome features. It also reminds of PyTorch and eager mode, and it's getting like much more flexible than it was. But this is more like advanced stuff, and maybe not so relevant right now. But just to let you know, for getting started with deep learning, I think there is no easier way to do that than with Keras, even though there are of course drawbacks to that as well. So can I ask one more question before I close? So who of you are actually would want to get your hands on code? Who want to try to build machine learning models themselves? 1, 2, 4, 5, 6. Yeah. 7, 8. Yeah, that's good. You should at least try, right? Who of you would work with someone who would do like the model building? Okay. Well, what about the rest? Not sure yet. Yeah, I would really suggest, because we're here today and tomorrow and we'll be writing some code. So I think even though you might have never written a line of code, it's still like it's a really great opportunity to get yourself into write some code, try to follow along. I can tell you, I don't know how you felt after Nick's presentation. I know this is a lot to handle, right? This is a lot to process. A lot of math, a lot of very complicated theory, and then tomorrow code. If you've never written code before, it's like a whole different world. But at least get yourself into it, process it, and then figure out stuff from there. If you are working in a team, and if you have someone who is doing the technical things for you, make sure that the communication is always good. I say this because I've been managing and mentoring projects for a while now, and this is like the most important thing, because people from different disciplines have different ways of doing things, right? And you need to make sure to communicate tasks very well, your data very well. You have to kind of use tools that allows you, the whole team, to have access to all the resources, for example, to the data, to the source code, to the models, to the weights, and so on. So I would suggest using some version control like GitHub or GitLab. Something like Slack, where you can communicate fast and easily. Another thing is that this might be, I don't know how relevant it is, but another very good tool to work with is Google Colab, and we'll be working with it tomorrow. Or today too, perfect. I like this because, when you write code, everything makes a difference. So your hardware, your software, your operating system, your IDE, your Python environment, the requirements that you have already installed on your laptop, the requirements that you need. And this makes it very hard, if you work collaboratively or doing workshops like that, it makes it sometimes really hard, to satisfy everything. So Google Colab is an in-browser notebook, and it allows you literally like to do everything within that notebook. So you don't have to install anything outside of that notebook. You just need like a Gmail account and Drive. You open that notebook and you can do everything inside. And the best thing about this, I haven't explicitly mentioned it, but I've said multiple times that we need a lot of computational power to train very deep networks, or not even deep networks. Like even if your image data set is I don't know, 50,000, you want to train it on a GPU. A GPU is a graphical processing unit, and it's typically things like that. So there's a difference between his and my laptop. There's no GPU in a Mac. There is a GPU here, and it's typically like for gaming. It's a graphical card, and it speeds things up. And turns out it's really awesome for deep learning. So it speeds up your training time many times. And you would always use a GPU, but you know, when I don't have a GPU here, you could run it on a CPU. I wouldn't suggest it if you have a larger data set or a deeper network. So you have to use things like GPUs or cloud. And Colab has actually a GPU integrated in a notebook that is free, which is the best thing, because typically you will have to pay for it. And two more things that I want to mention, and I think I have 3 minutes, which is perfect. FastAI. So if you want to get into deep learning, FastAI is a deep learning library. It's built on top of PyTorch, and those guys, I forgot his name. Jeremy Howard. He's amazing. So he and his wife, they did incredible tutorials on intros to deep learning, and this is the best source for domain experts to get into deep learning. They'll teach PyTorch, and they'll teach top-down. So you write code and you figure out the details later. And a lot of domain experts, a lot of people in research, a lot of people in medical imaging, doctors really kind of got into these courses and made incredible projects for that. So it's a really good way to get started if you want to write PyTorch code and FastAI code. Yeah.
FastAI and Keras on separate lines, but aren't they both the same idea?
If they're both the same idea,
aren't they both the reference for that line? Like in the
oh yeah, so FastAI is just a library, right?
So is Keras, right?
Yeah, Keras is it's an API. Yeah, it's kind of the same. Yeah, you could, but it's very different in practice. I think it's quite different. So you can do. I would recommend both. So it really depends on if you want to write Keras code or if you want to write PyTorch code. Because with Keras, you'll be writing Keras code. So it is a high-level API. So you'll be writing Keras code. You'll be writing deep learning in Keras code. With FastAI, I think you can also write FastAI code, but the overall framework is PyTorch. So you'll be learning to write PyTorch code. But yeah, you're right. Yeah, good point. And yeah, the last thing I want to mention is Kaggle. So luckily, we have a platform. If you want to get started with deep learning and machine learning, and you're looking for data sets, because everything starts with a data set, you can go to Kaggle, and it's a platform with literally, I don't even know, hundreds, thousands, I don't know, many data sets. So whatever problem you have, whatever task you're looking for, whatever data set you're looking for, they probably have something. Maybe not exactly what you're looking for, but something that might be useful for you. Yeah, so that's it. We have no more minutes, but okay. Do you have any questions so far before we get into a break?
Yeah.
Before we get into a break.
No questions? Break? Okay, let's do a break. Thank you, everyone.
Thank you, Suzana. So